Question 4.2 is similar to 4.1 in that it's asking us to calculate for this bar, which is undergoing fixed axis rotation around this fixed axis, what the velocity magnitude and acceleration magnitude are at point A. And again, this is linear velocity and linear acceleration as opposed to angular velocity and angular acceleration. So let me do a quick sketch. Okay, there's the bar, there's point A. It's at an angle theta from the horizontal, and that distance there is 2 meters. So R in this case is equal to 2 meters. Now, what makes this different from 4.1 is that now the angular acceleration isn't constant. Actually, we're given the angle as a function of time, so theta is equal to 0.3 t plus 0.018 t cubed. Now we can, rather than just think of that as being an angle, let's think of that as angular displacement. So where the displacement is 0 at theta 0. So this is angular displacement. And how does this relate to the angular velocity and angular acceleration? Well, the angular velocity, and omega is our symbol for that, is the time rate of change of angular displacement. So it's d theta dt. So in the same way that linear velocity is the time rate of change of displacement, angular velocity is the time rate of change of angular displacement. So we can now differentiate that expression, and we get 0.3 plus 3 times 0.018 t squared. And that is 0.3 plus 0.054 t squared. Now, angular acceleration, which is the other thing we need to calculate, and this is also a function of time, this is the second derivative of the angular displacement with respect to time, in the same way that linear acceleration is the second derivative of the displacement with respect to time. It's also just the first derivative of the angular velocity. So in the same way that linear acceleration is the time derivative of linear velocity, the angular acceleration is the time derivative of angular velocity. So we're just differentiating this again. And that gives us, well, that goes to 0. That's going to 2 times 0.054. What is that? 2 times 0.054, 0.108. So that's 0.108 t. So that's, you can see that the acceleration is linearly increasing with time, so I suppose this bar is doing something like, you see what I mean? So it's, the acceleration is increasing with time. Okay. So now we know the angular velocity and the angular acceleration is a function of time, and the question asks, well, what are the properties of the system at t equals 4 seconds? So we can shove 4 into these two expressions now. So 0.3, so I'm putting this into angular velocity expression, 0.054 times 4 squared. That gives us, so omega at 4 is equal to 1.164 radians per second. The angular acceleration, 0.108 times 4, is equal to 0.432 radians per second squared. Now it's exactly the same as the end part of 4.1. If we just go to our lecture notes, we can start by working out what the magnitude of velocity is, because there's only one component, that's vt. and we have an expression for the tangential component of velocity, r omega, and this is because it's a fixed axis rotation of a rigid body. There's no normal component of, no radial component of velocity. So that's what is it's 2 meters long times omega, which is 1.164 at 4 seconds. So that's 2 times 1.164 is 2.32, 2.33 meters per second rounded up. So that's the first part, because the magnitude of velocity is just the tangential component, because there's only one component. There are two components to acceleration, as shown here, the tangential and the radial. So let's work out what the radial is. That's the centripetal component. We're only interested in the magnitude of this, so we can ignore the negative sign. That's r omega squared. And that's 2 times 1.164 squared. So it's this times 1.164 is equal to 2.71 meters per second squared. So that's the radial component. The tangential component of acceleration is r alpha. That's 2 times what we calculated here, which is 0.432. So 2 times 0.432 is 0.864 meters per second squared. So on our diagram of point A, we've got an acceleration. They're both positive, so there's the tangential component is positive, so it'll be in this direction. That's the AT. Then we know that the radial component is in this direction. So our total acceleration vector looks like that, and its magnitude is just calculated by Pythagoras, AR squared plus AT squared, which is equal to, let's just do that quickly, square root of 2.71 squared plus 0.864 squared. And that gives us 2.84 meters per second squared as our total magnitude. That's the length of that. And that's, I think, all for that question.